Hello, everyone. Welcome to the third lecture of Dynamic System 1. So today we will be discussing work and energy, which is the second way to solve problems in kinetics. In the previous lecture, we discussed the one way to solve problems in kinetics, which was the Newton's second law. And in this lecture, we will discuss this new way, which is the work and energy. So to just give you an idea of the previous lecture, we will just summarize the previous lecture here. So in the previous lecture, we discussed introduction to kinetics and its applications. And then we also discussed the Newton's second law, which is the base of kinetics. So according to the Newton's second law, the acceleration of particle is proportional to the resultant force acting on it and is in the direction of this force. So if you look at this figure here, we are applying a force F on a body of mass m, and the body is moving in the direction of the force with acceleration a. So then mathematically we can write the Newton's second law in this form. So it is F equal ma, and this is a vector equation. So F is a force which is vector, m is a scalar which is mass, and a is the acceleration, which is again a vector quantity. Now, in case of multiple forces, you can also write the equation of motion, which is the Newton's second law. So when a particle of mass m is subjected to the action of forces F1, F2, F3, as you can see in this figure, that this particle of mass m is subjected to three forces here, F1, F2, and F3, and whose vector sum is summation of all the forces. So if you sum these three forces, and because force is a vector, so this will be a vector sum. So this the Newton's second law can then be written in this form, that summation of all the forces should be equal to ma now, and the direction of acceleration will be in the direction of this sigma f. Now this is again a vector equation which we can write in different directions. So we can write this equation in x direction, which is summation of all the forces in x direction equal to max, summation of all the forces in y direction equal to may, and summation of all the forces in z direction equal to maz. So this is the Newton's second law in x, y, and z direction. Again, these are some important equations. So because acceleration is a vector, so we can write this in this form, which is ax I, and I is a unit vector along the x-axis, ayj. So ay is the component of acceleration in the y direction, and j is the unit vector of in y direction, and az is the component of acceleration in the z direction, and k is the unit vector in z direction. And if you know the component of acceleration ax, ay, and az, so then you can use the Pythagoras theorem to calculate the magnitude of the acceleration. Similarly, a force can be split into x, y, and z component, and then you can calculate the magnitude of the force from its component using again the Pythagoras theorem. And these are equations in three dimensions. So if you have x, y, and z component, you can also write these equation in two dimensions. So then we will just skip the z component of acceleration and force here. So in the previous lecture, because we were dealing with the forces, so we discussed different type of forces there, and the first type of force that we discussed was a spring force. So as you can see in this figure here, that for a given x, so x is the either stretch in a spring or compression in a spring. So for a given x, spring force can be calculated using the Hooke's law, and the Hooke's law is F is equal to kx. So F here is the spring force, k is the spring constant or stiffness of the spring, and x is the stretch or compression in the spring. So where k is the spring constant and the unit of k is Newton per meter. So as you can see in this figure here, that if you stretch the spring, as in this case, so the spring force will be opposite to the stretch, so it will be a pulling force. And if you compress a spring, as in this case here, so the spring force will be opposite to the applied force, and the spring force in this case is a pushing force here. Again, we also discussed about the friction force, which is again sometime you need to calculate for the numerical examples when you are solving numerical examples. So as you can see, you can understand the friction force from this diagram here, which is the diagram between the applied force, which is on the x-axis, and the friction force is on the y-axis here. So if you apply a force P on the body, so the body will experience some sort of friction force. So initially the body will be in rest, and if the applied force is increasing, so the friction force is also increasing, and at one point you will reach this F maximum, which is the maximum friction force, and the maximum friction force can be calculated using this mu Sn. So n is the normal force, and mu s is the coefficient of static friction, and this is the point at which the motion will start and the body will start to move, and therefore we call this impending motion. So from this point to this point, or up to this point, this was the region where there was no motion of the body, and therefore the friction is what we call is a static friction, and this F maximum is the maximum static friction. So if you want the body to move, you will have to apply a force which is greater than the maximum friction force. And once the body start to move, so the friction force will change to kinetic friction, and we represent this by Fk. And Fk is again can be written as mu Kn. And then you can see from this point onward, this is a region where you have a kinetic friction, because we have a motion here. And as you can see in this diagram, the kinetic friction is always less than the maximum static friction. So again, you can write these equation here, that F maximum is equal to mu Sn, and mu s is the coefficient of static friction, and Fk is equal to mu Kn, where mu k is the coefficient of kinetic friction. And this is also a very important point to understand, that the coefficient of static friction is always greater than the coefficient of kinetic friction. And finally, we also discussed the gravitational force, that which is the weight of the body. So because in the y direction the acceleration is g, which is 9.81 acceleration due to gravity, and the weight of the body is then mg, which is the mass times the g, which is the acceleration due to gravity. Okay, so if we now start the today lecture. So in today lectures we are planning to cover the following topics. So the first one is that we will define and then we will discuss the procedure of how to calculate work, and then we will discuss a few cases. So the first case will be how you will calculate work for a constant force, how you will calculate work for a spring force, and how you will calculate work for weight or gravitational force. And then we will discuss this very important principle, which is the principle of work and energy, which is another way to solve the kinetics problems. And finally, we will also discuss some potential energy, which will automatically go into the principle of work and energy. So again, we can discuss two type of potential energies. One is a gravitational potential energy, which is due to gravity, and one is elastic potential energy, which is due to the spring forces. Okay, so now as you can see here, that if you consider a force F acting on a particle at A, which moves along the path shown. So now we want to define what is work. So in this case, what you are doing, you will consider this this path here. So if we consider this path here and assume that this was the position of particle, the particle was initially at position A, and then it moved to this another position, which is A dash, and a force is applied some sort of in this direction here. So this is the applied force. Okay, so force F acting on particle at A, which moves along the path shown. So this is the path along which the particle is moving, and a displacement vector from A to A dash can be right in this form, which is a delta R. In this case, what we can write, that we can choose an arbitrary point, which is O point here, and then we can write that the position vector of point A was R, and the position vector of A dash will then it will become R plus dr. And again, you can see that this is, if you add R and delta R and dr, so you will get R plus dr here. Okay, so R is the position vector of particle at point A. So as you can see, this R is the position vector of this A from origin O, and origin O is just an arbitrary point, and dr is the differential displacement from A to A dash, and then the body moved from A to A dash, which is a small displacement from A to A dash. So now if we want to calculate the work done by this force F during the displacement dr is defined as this. So we will write that the work is d into capital U. So d here is because we want to calculate the work done in this differential displacement, which is a small displacement here. So therefore we are writing this is du, and du is just the scalar product of F and dr, so which you can write is a dot product into dr. So this is you can say is a dot product between F and dr. And we know that if you take a dot product of two vectors, it becomes a scalar. So du is a work which is scalar, and which is the dot product of two vectors. So one vector is F, which is force, and another vector is dr, which is this small displacement between point A and point A dash. Okay, now again we know that if you consider two vectors A and B, so we know that the dot product between two vector is A, magnitude of the first vector, magnitude of the second vector, into cos theta, where theta is the angle between the two vectors. So if we have these two vectors A and B, so this is how we can write the dot product between the two vectors. So in this case, because we have two vectors here, one is F, one is dr, so then the du can be written as F, and F is the magnitude of this F, and if we say that ds is the magnitude of dr, so then we can write F ds cos alpha. And in this case, you can also write this, that ft into ds. So now we will explain how is this this become ft into ds, and what is this ft. So if you look into this figure here, so this is our particle P, and the applied force is is in this direction here. So this is the applied force, and the body is moving in this direction here. So this was our dr. And the magnitude of this dr is ds. So this is the magnitude of this dr here. And again, we can see here that this is the action, the line of action of this force, and this alpha angle is this angle here, which is the angle between F and dr. So this alpha is coming from here, which is the angle between F and dr. Okay, so now we can split this this F into two components. So one will be in this direction here, and one will be in this direction, or in this direction here. So one component will be in this direction. This will be the F normal force, and we call this force is ft, which is tangential force. We call this tangential because this is tangent to this path, and the tangential force is in the direction of the dr, as you can see from this figure here, and Fn, which is again the component of this F in this direction here, which is the normal to the path. And again, we can write this Fn, which is this angle is alpha, so this angle is also alpha here, so this is also alpha here. So then we can write this ft, which will become f cos alpha, and Fn will become f sin alpha. So this is how you can split this F into two components. So Fn and ft. So ft is in the direction of the dr, and Fn is perpendicular to dr. So as you can see in this case here, so this F and cos alpha, which is F cos alpha, become ft, and then ds will stay there. So this means that if you want to calculate the work, it will become equal to the force in the direction of the displacement and into the displacement. This is how you will calculate the work done here. So where alpha is the angle between F and dr, as you can see in this case, that this alpha is the angle between F and dr. ds is the magnitude of dr, and ft is the component of force in the tangential direction or in the direction of dr. Because if you look at this this figure here, so f t was here and Fn was here, and then this is the alpha angle. So you can see that this ft is tangent to the path and Fn is normal to the path. So if you want to calculate the work done, it's really important to understand that the total force is not important here. The important force here is the component of the force which is tangent to the path, or which is in the direction of the displacement. And again, because in this case Fn is normal to the path or normal to the displacement, and it doesn't work. So the work from Fn is 0 here, and ft is doing all the work because it is displacing the body, but Fn is doing no work because it is not displacing the body. Okay, so now we can define the unit of the work. So we derive this equation here, that the work done by force F during the displacement dr is defined is this. So du equal to F dot dr, which is the dot product between force and displacement. And then we can write this, that F ds cos alpha, which is ft into ds, so which is tangential force into the ds, which is the magnitude of the displacement. So if you want to write the units of the work, so we know that this unit of the force is Newton, and ds is displacement, so its units will be m. So then the SI unit of work are those of force, which is the unit of force, times the displacement, so which is meter here. So the unit of work will become Newton meter. Now the units is given the special name joule, which is defined is the work done by a force of 1 Newton acting through a distance of 1 meter in the direction of the force. So if you consider this equation, that du equal to ft ds, so then you can say that 1 joule is a force which is equal to 1 Newton into 1 meter. So this is the definition of the joule here. Okay, now we can define how you will calculate the total work from this differential or small work. So again, we know this this basic definition of the work, that work the differential work can be write ft into ds. So this is a differential work, which is a small amount of work, and this can be right is the tangential force time ds, and ds here is the magnitude of the displacement here. So again, if you have this equation, that du equal to ft into ds, so if you integrate this equation and this equation here, so this will become u, a capital U, and then this equation will become s1 s2 ft into ds. So this is again equation is telling us that if you want to calculate the work, you will integrate the ft from s1 to s2. So now in order to carry out this integration, obviously you will need to know the relation between ft and s. So for example, if you consider this type of relation here, that if on the x-axis we plot s here, which is the displacement or distance, and on the y-axis if we plot ft, so in this case if we have this type of plot and you are interested to calculate the work from s1 to s2 here, so you are interested to calculate this work here, and now we know that the differential work, which was this small work here, and this is our du, and which was ft, which is just the so this is just a triangle, and because the thickness of this triangle is very small, so we can say that if this side is ft, the other side is also ft, because the length is so small, so we can ignore the change in length here, and therefore the total work, which will be the area of this this small triangle, you can write this ft time ds, and the thickness here is ds, so s will become ft into ds. And now we want to calculate this total area under the curve from s1 to s2, which will be the work done. So which you can do by this equation here, that you will integrate the ft from s1 to s2 with respect to s. So this will provide you with the work. Okay, so now we will try to use this equation for different cases, so it will be get clearer how we can use this equation for some practical problems. Okay, so now in this case, if you want to calculate work for a specific example, you will always begin with the definition of the work, which is this equation here, that u is equal to s1 to s2 and ft ds. So this is the basic definition of the work, that work from s1 to s2 is always equal to ft ds. So now, for example, we are interested to calculate the work associated with a constant external force. So if you consider this body here, and you apply a force P on this body, and the force P move the body from this position 1 to position 2, and the distance from this position 1 to position 2 is L here. The coordinate system are given here, so this is our X, this is our Y. And again, we know that the dr, which is the displacement, is in this direction. The applied force is not in the direction of the displacement, but it is at some angle to the displacement here, and the angle here is alpha here. So now we want to calculate the work done by this force when the block move from position 1 to position 2. So again, we will start with this basic definition of the work, that U12, which is the work done by this force from 1 to 2, from position 1 to position 2, and this will be equal to S1 S2 Ft ds. Now what is Ft? Ft is the tangential force, which is the component of the force which is in the direction of the displacement. So in this case, as you look at P, you can split this into two components, and you can say that you can split this into two components. So one component will be here and one will be here. So this this is Ft and this is Fn. So we know that Ft will become F cos alpha and Fn will become F sin alpha here. Okay, so in this case, because the body is moving only on this plane here, the body cannot move in the y direction. So we know that this Fn, which is the normal to this path, is doing no work. The only force which is doing work is this Ft, which is F cos alpha. So now we can write this equation that U12 will become equal to, so again we can write that it is S1 to S2, and S1 is the displacement which is here, and S2 is the displacement which is here. So Ft in this case, as you can see, it is Ft, which is P cos alpha, and you can write ds. Now if you look at this integration, it's a very straightforward integration, because P cos alpha is not a function of displacement. So the P cos alpha is constant with respect to S. So this means that we can take it out of the integration. So the integration will become just S1 to S2, just one will left here, and which you can integrate. So P cos alpha, and it will become just S, and then the limits are S1 to S2. If you just put the limits here, upper limit minus lower limit, so this will become P cos alpha, and as you can see in this figure here, that S2 minus S1 is nothing but just the this L here. So this means that that we end up with this equation here. So this means that the work done by a constant force is equal to P cos alpha into L. So this means that if you take the component of the force which is in the direction of the displacement here, which is P cos alpha, and then you multiply with the displacement, which is L, so you will get the work done from 1 to 2. Okay, so in this case, because in the previous case the force was constant, so it was relatively straightforward. But now we want to calculate the work associated with a spring force here. So the work done on a body by a spring force is the body displaced from initial position x1 to final position x2. So as you can see in the case of a spring, that if you take a spring here, and if this is the undeformed position of the spring, and you apply some force on the spring and you try to move the spring in the x direction. So this is the coordinate system. So you move the spring in the x direction here. dr is the displacement here. So what will happen? You are generating force in the spring, which will be opposite to the applied force here. So in this case, the spring force we can write is kx, which is the spring force, and we are writing this in this form because this is the Hooke's law, which is F is equal to kx. So as you can see here that the spring force here is not constant, but it's changing with x. And if you try to plot the spring force as a function of displacement here, so this is how you can write it. So if you plot the displacement on the x-axis and you plot the spring force on the y-axis, so this is our spring force here. So we know that the spring force, if the displacement is 0, the spring force is 0. That is if the spring is unstretched, so the spring force is 0. If you apply force on the spring, so you are stretching the spring here, and you are creating some force in the spring, so which will be that force here. And if you increase this stretch in the spring and you change this to x2, so obviously you are increasing the spring force here, so which will become this force here. So this means that the spring force is changing according to this equation here, which is F is equal to kx, and F is the spring force here. Okay, so now in this case, now you want to again calculate the work which is associated with this spring force. So you are applying force on the body and you are displacing the spring, but now you want to calculate the work done by the spring force, not by the applied force. This is important point, that you want to calculate the work done by the spring force. So again, you will start with the basic definition of the work, which is U12 equal to S1, S2, and Ft ds. So Ft is the force which is in the direction of the displacement here. So in case of the spring, we can write here that here instead of s we are using x, so we can change s to x, so x1 to x2, and then the spring force will become this, the force here is the spring force, and then again it will become x. So now we want to calculate the spring force from for example from the displacement x1 to displacement x2 here. Okay, so in this case now we can write that the spring force is equal to f this kx here. So we can write this equation x1 to x2. Okay, now in this case there is one important point that you need to understand, that because the spring force is in the opposite direction to the displacement, so therefore we are taking the spring force as negative because it is in the negative direction and the displacement is in the positive direction. So what we will do, we will just use it something like this. So kx into dx, because here dx and kx, which is the spring force, is in the opposite directions, and this is just so if you just write this statement, the spring force opposite to dx here. So that's why we have this negative sign here. Okay, now we can integrate this equation here. So in this case, because we are assuming that k is constant here, so you can take this minus k outside, and then this will become x1 to x2, and the only thing which will left inside the integration will be x. So if you just do the integration, it will become x squared divided by 2, and then you put the limits of integration, which is x1 to x2 here. That you just put these limits, so it will become k by 2 and x2 square minus x1 square. So simple, you can write this half k x2 square minus x1 square. So in case of spring, the work done when you move the body from position x1 to x2 is this equation here. So minus half k, which is the spring constant, and x2 square, which is the final position of the spring, and x1 square, which is the initial position of the spring. So this and because in the previous case, in the case of just a constant force, it was constant, so inside the integration was just 1. But in this case, obviously the spring force is changing with x here, according to this law. So therefore we are writing this equation in this form here, that the spring force will become kx, and then the work done from 1 to 2, which is this position x1 to x2, will become minus half k x2 square minus x1 square.